in the energy transfer that we're talking about, we're going to either use palmitic acid or glucose, and the energy that's stored within them in the chemical bonds, and we're going to transfer that energy, right? Because the energy cannot be created nor destroyed. So we're transferring that energy to take adenosine diphosphate and an extra phosphate and combine those guys into ATP. So we're going to oxidize palmitic acid, we're going to oxidize glucose and a whole bunch of other stuff along the way to eventually transfer that energy into ATP, the main molecule for biologic work. If we were to take just a very generic basic cell, so here's our plasma membrane, the barrier of the cell, and we have, we'll have a nucleus and all that other kind of fun stuff, but then we'll also have a cell organelle called a mitochondria down here. Now, palmitic acid has, because it's a fatty acid, it has its own issues that we'll talk about towards the end. But basically, whether it's glucose or palmitic acid, we're going to break this down, and glucose gets broken down outside, but we'll eventually try to get inside of the mitochondria to have this one molecule that I'm just going to have a star, and that's acetyl-CoA. So we want to get acetyl-CoA into the mitochondrial matrix. Now, for the fatty acid, palmitic acid, we're actually going to attach a coenzyme A first out here in the cytosol and get it transferred in, and then make a whole bunch of acetyl-CoAs after that. And then from the acetyl-CoAs, then a whole bunch more stuff will be oxidized and oxidized and oxidized, and a whole bunch more ATP will be made from there. The first speed bump that we're going to talk about to get to acetyl-CoA is with glucose, and that process is glycolysis that takes place in the cytoplasm or the cytosol of the cell. In glycolysis, we start with glucose, that's 6 carbons, and there's a whole bunch of hydrogens and oxygens that are also attached here. I just want to keep track of the carbons in this particular diagram. We're using an ATP and rearranging some of the molecular structure, and we're adding a phosphate that came from the ATP. So we actually use ATP in this first part of glycolysis. Then more chemical reactions happen until we get fructose 6-phosphate. And then this is where a very important enzyme, phosphofructokinase, or in McCardle Katch's book is called, they abbreviated it as PFK, for phosphofructokinase. It's a limiting enzyme in that, man, if this isn't working, everything else is kind of bogged down, which goes back to the other cellular regulatory responses of when to make PFK, when to release PFK, and to make sure PFK is operating at its optimal level. This step here, right, is also where we're going to have another ATP used in glycolysis, where now we have this fructose 1,6-bisphosphate. Well, this is where, I kind of look like get out our cells, I should say, get out their inner Bruce Lee, and they karatecize or chop in half this 6-carbon molecule into 2 3-carbon molecules. Each of them has their own phosphate attached to them. And this last one is glyceraldehyde 3-phosphate. And the glyceraldehyde 3-phosphate is what's going to continue on into the second part of glycolysis. The second part of glycolysis is where we're going to take these glyceraldehyde 3-phosphates, the G3Ps that we just talked about at the end of glycolysis 1. And so again, we have 2 of them, right? Because the original 6-carbon glucose molecules got chopped in half into the G3Ps, each with the phosphate attached to them. We're going to have another inorganic phosphate come in and attach. And this is the first time where we see NAD plus come in, and with this chemical reaction is going to take electrons and hydrogen, right? So we have a G3P here and a G3P here, so we're going to make two different NADHs that are both carrying electrons and hydrogen. Those NADHs that are carrying the electrons and hydrogen are going to take the electrons and hydrogen to the electron transport chain that we'll talk about towards the end. Think of NAD plus and NADH kind of like an Uber or a Lyft, right? This chemical reactions happen, it gets on its phone, it says, hey, I need NAD plus to come over. Looks like a great price. Yeah, come in, take some electrons and hydrogen. We're all good. And then it goes and drops it off from the cytosol and goes to the electron transport chain in the mitochondria and drops off the electrons and hydrogen. Well, then now the Uber's empty, right? It's in the form of NAD plus, waits for its next job, goes, picks up more electrons and hydrogen, takes them to the electron transport chain, comes back to more chemical reactions, picks up more electrons and hydrogen, takes them to the electron transport chain all night. From here, we have a series of more chemical reactions. We have substrate level phosphorylation here, where this ADP is going to come into the chemical reactions, and as you can see, it's going to take one of the phosphates to generate ATP. And so there's two ATPs, and then more chemical reactions, and our last phosphate is taken off with ADP to generate another ATP, and we're left with the 3-carbon molecule pyruvate at the end. Now, this pyruvate is going to make its way into the mitochondria. KIN et al. Tells us that, while glycolysis is technically done at this stage, pyruvate's still got a little bit more job to do. So remember, glycolysis happened outside of the cytosol, and if this line right here represents the outer membrane of the mitochondria, as pyruvate goes in to enter the mitochondria through the outer membrane, we see this wonderful Uber driver right out here, NAD plus, to come in and take the electrons and hydrogen to form NADH, right? 2 of them. And those NADHs, just like in glycolysis, are going to head over to the electron transport chain to drop off the electrons and hydrogen there. Also, we see this CoA here. So the sulfur that's attached to a coenzyme A is attached to this now 2-carbon molecule, and we have what we're looking for from the jump street, right? We're trying to get that acetyl-CoA. Oh my gosh, this looks like a scary diagram. Let's not worry about it too much, okay? Just to show a big picture, membrane of the cell, here's the cytosol, and here's the nucleus, and this structure right here is the mitochondria. This is our same diagram, just the mitochondria portion is blown up just a little bit for us. So we have our fatty acid with coenzyme A attached, right? We're gonna go through our fatty acid beta oxidation, and we see all these loops. That's gonna make more sense in a minute, and we're left behind with our acetyl-CoA. In beta oxidation, the first step is dehydrogenase, an enzyme that's going to take out water. It's going to take it out, right? So it's going to take out, really specifically what we're worried about is the hydrogen and electrons. So here we see this other guy, FAD and FADH2, which, okay, if NAD and NADH was Uber, FAD and FADH2, it's Lyft. Does the exact same job, but just different companies. In this first step, it's going to take some electrons and hydrogen. In the second step, we're going to add water. Then another dehydrogenase is going to act in the third step, and this is where we see our NAD plus come in and take electrons and hydrogen and have our NADH. And the fourth step is kind of cool because it really has a really fun enzyme attached to it. I wish I memorized it off the top of my head, but it's just fun to say. I'm going to cheat and look at it though. It's beta-ketoacyl-CoA thiolase. What that does is it takes the last 2 carbon atoms with the coenzyme A attached Oh my gosh. Leaving behind acetyl-CoA, our magic acetyl-CoA. And then this long chain that's left of the fatty acid goes back to the beginning. AbChem 2019A and McCardle Catch and Catch get into this stuff a little bit, but palmatic acid or palmitate has 16 carbons in it. And we got a whole bunch here. Let me speed this up real quick. So in our beta oxidation, the first thing that's going to happen is FADH is going to come in and it's going to take 2 hydrogens and the electrons that come along with it. Next part, right, we have our hydration part come in. So water is going to come in, but water gets split. So it's going to come in and look like that. Then, so the NAD plus is going to come in and take this hydrogen electrons and this hydrogen electrons right here. And then our last step is we get our Bruce Leon and we're going to cleave, or we're going to chop off this molecule right here. Bear in mind, I'll just say we're R for right now for our organic chemistry needs, and picking up right about here. I'll see you in a second. So after our Bruce Lee cleavage action karaticized chops, we originally had a 16 carbon molecule. Now we're left behind with a 14 carbon molecule. And off here, this got chopped off. So this is acetyl-CoA. So we have 1 acetyl-CoA and our leftover 14 carbon molecule. Well, that same process that just happened with all of these, it's just going to set up again, right? So we'll chop this guy off and be left with a 12 carbon molecule and have a second acetyl-CoA. And it'll happen again, and then it'll keep, and then we'll have 10 left and 8 left and 6 and 4 and 2. And well, 2, well, then that's just our acetyl-CoA, right? So from our original 16 palmitic acid, that's gonna get chopped down and oxidized and oxidized and oxidized and oxidized 8 different times. So we'll have a total of 8 acetyl-CoA molecules from the oxidation of palmitic acid. Thanks to Kenny et al. 2015, we know that the acetyl-CoA that we just made a whole bunch of in the mitochondrial matrix, it's going to join in the citric acid cycle, or take part in the citric acid cycle, or drive the citric acid cycle. Our 2-carbon acetyl-CoA is going to join with a 4-carbon molecule that's already in the citric acid cycle to make our 6-carbon, hey, you guessed it, citric acid. And a whole bunch of chemical reactions take place. And within these chemical reactions, big picture, each acetyl-CoA that comes in has the citric acid cycle turn once. And each time we have all these different chemical reactions take place. For 1 molecule of glucose, the citric acid cycle is going to turn twice. But for every single round, 1 ATP, 1 FADH2, 3 NADHs. There's going to be 2 rounds per molecule of glucose and 8 rounds per molecule of palmitic acid. So far, we haven't made a whole heck of a lot of ATP. The electron transport chain, that's where the magic happens. That's where we're making the majority of our ATP. So just to give you a quick snapshot here, this double line here, that represents the outer membrane of the mitochondria. So outside here, this is the cytosol. Inside here is the mitochondrial matrix. And the space in between these two guys is the inner membrane space. This inside membrane of the mitochondria is called the cristae. So what happens is the NADH is going to drop off, its electrons and hydrogen to the first protein or cytochrome in the electron transport chain. And the electrons and hydrogen, they pass from one protein to the next, right? So this first protein gets the electron and hydrogen and passes the electrons and hydrogen to the second protein, which passes to the third, passes to the fourth, kind of in a downhill or waterfall-like fashion, till we get to the end of the protein, or the last protein or cytochrome on the electron transport chain. Doesn't sound like a whole heck of a lot yet, just bear with me. As we see here in the diagram, FADH2 does not drop off its electrons and hydrogen, its cargo lift, at the first protein. It's actually at a lower free energy level. So FADH2 doesn't quite drop off or provide as much energy through oxidative phosphorylation as NADH does. Still does quite a bit, but just not quite as much. Same process. Along the way, the electrons and hydrogen get separated, which causes a big buildup of hydrogen ions in the intermembrane space, not so much in the mitochondrial matrix. So we have a hydrogen ion gradient. The last thing to accept the electrons is oxygen. It's literally the reason why humans need to breathe in oxygen and use oxygen. So the oxygen takes that. Okay, well, wait a second. We still haven't made any ATP yet. I thought this was how it all makes. Well, there's this really cool enzyme here called the ATP synthase complex. And it uses that hydrogen ion gradient that we just made. So the hydrogen ions want to go from an area of high concentration to an area of low concentration. So in this case, goes from the intermembrane space to the mitochondrial matrix. So when it goes through, it causes this enzyme to spin or basically change, have a conformational change, which I said before is a fancy term for changing shape. So it'll take ADP and a phosphate to make, you got it, ATP, tons of it. For each NADH, it's about 3 different times or 3 different places that will make ATP, and it's 2 times for FADH2 because it's at a lower free energy level. The electrons form with the oxygen. The hydrogen is going to go hang out with the oxygen, and they all combine together to form water. Where are we going to get more ATP from? Well, as we know from Ricardo Catch and Catch, before we get into this magic number here, just want to point out that, yeah, it's about 3 ATPs for every NADH going through the electron transport chain and 2 for every FADH2. However, on average, right, because we know while energy is not conserved or lost, energy is also working to a larger degree of randomness as well. So a lot of that energy transfer, each time we have energy transferred from one chemical to another, we're actually going to lose some of the energy to the environment. On average, it's really 2.5 molecules of ATP for every NADH, and is 1.5 molecules of ATP for every FADH2. So if you add everything up, all the NADH and FADH2s and the substrate level phosphorylations from glycolysis in glucose, citric acid cycle from glucose, and the electron transport chain from glucose, there's a net gain of 32 ATPs. Taking that same process in mind, AbChem 2019 tells us that through the process of beta oxidation, the citric acid cycle from palmitic acid, and the electron transport chain from palmitic acid, 1 molecule of palmitic acid, if it was completely oxidized from point A to point B, would result in 129 molecules of ATP. Just sheer volume, palmitic acid, being the fatty acid, is going to have much more stored or potential chemical energy in it than a molecule of glucose. With glucose, we have our phosphofructokinase that we already alluded to as a limiting factor, and oxygen in and of itself. Well, what do I mean by oxygen is a limiting factor? Remember that oxygen was the last thing to catch the electrons and hydrogen in the electron transport chain. So without oxygen there, all of the Uber drivers and Lyft drivers, the NADH and the FADH2, are stuck. it's kind of like a domino effect, right? If there's no oxygen here, that means this last protein in the electron transport chain has to be stuck, which means this protein stuck, and this protein stuck, and stuck, and stuck. Now our NADH is stuck holding the electrons. Same with the FADH2. It's stuck holding the electrons, and everything's stuck in the reduced state. It all kind of shuts down. Well, that's where fermentation comes in and lactic acid buildup and all that kind of stuff, but that's a different time. Another limiting factor for this glucose or carbohydrate pathway is glycogen. Glycogen storages are limited. Palmitic acid isn't exactly a walk in the park either, because it's super slow. And there's some slow things because, well, I mean, it takes a long time to get from where it's stored, to travel through the blood, to get to the working tissues. Whether it's albumin, that's part of the transfer process, it's not easy. And getting the triglyceride to be broken off and cleaved into the individual palmitic acids, to be broken down and add the coenzyme A to it. It's a very, very slow process. Both of these pathways are dependent upon the electron transport chain, so oxygen is going to be a limiting factor in both. Specifically for glucose, that's where we see our big, or glycolysis, I should say. That's where we see our big buildup of lactate. The beta oxidation doesn't come with that, but our beta oxidation is definitely going to be affected by a lack of oxygen. Although oxygen is used directly, indirectly it would be affected because the electron transport chain is going to shut down because our Uber drivers and Lyft drivers are full. And thank you to Kenny et al. And McCardle et al., both 2015, for those nuggets of information. As alluded to previously, there's not one pathway that is have your cake and eat it too. Both pathways complement one another, and neither pathway would suffice on its own for our energy demands and exercise. Yes, our carbohydrate pathway is much faster, but when we run out of glycogen stores, we're going to need to oxidize fat. Additionally, when our anaerobic tissues don't have oxygen delivered to it right there, we're going to have a huge buildup of lactate. Not only lactate, but also hydrogen ions as well. And those hydrogen ions are going to affect the pH, which affects the whole chemistry of everything and potentially shuts down as another limiting factor. And at the same time, we still need our carbohydrate pathway because it's much faster than oxidating fat. And also, fat is needed as a fuel source because it stores a much higher amount of stored energy than its carbohydrate counterparts. And thank you very much to McCardle et al. 2015 for that nuggets of information. It's been fun, but all good things must come to an end. Thank you much.